All right, good time of day, everyone, and welcome to this new MLIR open meeting. And today, Bixia will present the work that has been done on PyTACO, which is an end-to-end use case for the Sparse Tensor compiler. Bixia, the floor is yours.
Okay, thank you. So my name is Bixia Zheng. I'm from Google. Today, I'm going to tell you how we implement domain-specific language called PyTACO using the MLIR support. So this is an end-to-end use case for the MLIR Sparse Tensor compiler. So in this talk, we will look at what MLIR-PyTACO is, and then we will look at the sparse tensor computation support in MLIR. After that, we will talk about how we use this support to implement PyTACO. And at the end of the talk, I will show you where the source codes are and then some ongoing work for the project. So TACO represents the Tensor Algebra compiler. It's an open source compiler, and it's developed and maintained by a group of MIT and Stanford students. PyTACO is a Python-based domain-specific language for using the TACO compilers. So we implement this domain-specific language using the MLIR Python bindings. So in particular, we support the index notation-based tensor algebra syntax, as well as the tensor IO syntax in the DSL. So we'll talk about these two syntax in more detail. So let's first look at the index notation-based tensor algebra syntax. It has a mechanism for you to define a tensor by specifying the size for each dimension, as well as the sparsity for each dimension. And the sparsity for dimension can be either compressed or dense. In this example here, we define a tensor called A with 2 dimensions, and the size for the dimensions are 2 and 3. And the first dimension is compressed, while the second dimension is dense. Index var is a way to represent a dimension in the iteration space. So in this example, we use an API from the language to create 2 index var and name them as I and J. Using tensor and index var, we can write tensor access expressions with the tensor name and then the index var inside the square brackets. In this example, we write expression Aij. It has the meaning, it tells that the tensor A has 2 dimensions that are related, provide data for the iteration space, iteration dimension I and J. So it essentially says A has 2 dimensions, and they should have the same size as the I and J dimension in the iteration space. Then we use operators to join tensor access expressions. We support some basic arithmetic operation like addition, subtraction, multiplication, and division. In this example, Aij plus Bij represent an element-wise operation between 2 tensors A and B. And the 2 tensors are both 2-dimensional. And if we assign this value to a tensor access expression Cij, it means we do an element-wise assignment. That means the result tensor C has exactly the same dimension as A and B. So we can also express a reduction using this syntax. And reduction is, we only support one reduction operation, which is the add operation. And the dimension being reduced is implied by the fact that a dimension used in the source expression doesn't appear in the destination tensor access expression. So we will look at that. We have more example for that in this talk. The domain-specific language also supports reading in tensor data and outputting tensor data. Coordinate format is a way we use to represent sparse tensor values. It basically lists all the coordinates and the non-zero values for the tensors. So the DSL supports two variants of the coordinate formats. A matrix market format is only for describing a sparse matrix, two-dimensional tensors. And the Frost format can support more general tensors with any dimensions. And the format of the tensors is implied by the suffix of the file names. So in order to read in a tensor, we have this API called read, where you can provide the name of the tensor file and then provide a list of sparsity for each dimension of the tensors. This means the tensor itself implies the rank of the tensor. And then this has to match with the sparsity list in the provide for the read functions. So the example I have here essentially read a file and construct a complex dense tensor, a two-dimensional tensor for A. The write method is used to output a tensor, and you provide the name of the tensor, the output file, which implies the formats of the output, and then the tensors you want to output. So the DSL also supports you to construct a normal tensor from a Python array, and the method is called from arrays. We'll look at how we can use this language to express the sparse matrix vector multiplication from for scientific applications. So in this example, the first line, we import the MLIR-PyTACO libraries. So and then we import the NumPy library. Then the next two lines, we define two formats. The first format is a compressed sparse row tensor format. It's a two-dimensional tensors. The second format, DV, is a dense vector format. After that, we prepare the tensors for the computation. We read in the data to for tensor A and construct a compressed sparse row format for the tensors. Then we generate random NumPy, use NumPy to generate random data to construct tensor vector X and Z. And after that, we define a vector Y to hold the results. And then we define the two-dimension I and J for the iteration space. After that, we write the tensor expression as yi equal to aij multiply xj plus zi. So this expression means we perform a multiplication, matrix and vector multiplication using I, A, and X, and then perform a reduction operation on the J dimension. After that, we add in the this resulting vector with vector Z, and produce the result and write it to Y. The last line in this file is to write the content of Y in a float format to a file. So that's how we use the this domain-specific language PyTACO to write express a tensor computation. We have just looked at the syntax in PyTACOs. Now I want to talk about the sparse tensor computation support in MLIR. So we all know that tensor is a first-class citizen in MLIR data type. Here, the first line says a tensor with a two-dimensional tensors, and the size is 3 and 4 for the dimensions, and the element type is double. Then we can use sparse tensor encoding attributes to annotate the tensor type to make the tensor to specify the storage format for each dimension in the tensor. So in the second example here, we define a sparse tensor encoding called CSR, compressed sparse row format. And that is a two-dimensional format with that the first dimension is dense and the second dimension is compressed. We annotate this CSR to the tensor and then make the tensor to tell how we want to store the value for the tensors. And the third example is just another case to define a two-dimensional tensor sparsities, as it's called a double compressed sparse row format. So in this format, both dimensions are compressed. So that's how we represent tensor and sparse tensors data type in MLIR. So MLIR also has the Linalg dialect, which has a generic op that is very close to what we need to implement the DSL. Here I show the first line shows tensor expression in the DSL. It performs an element-wise operation on tensor A and B. They are both two-dimensional, and then perform an add reduction on the J dimension and write the result to tensor C. Note that A and B, the index on A and B are a little bit different. While A has index I and J, B has index J and I. It means the order, the tensor storage dimensional, it represents the order that the dimensions are stored in the tensors. So in tensor B, the first dimension J is stored before dimension I. So in Linalg, we can use Linalg generic op to represent these computations. So in Linalg generic op, it has a component called index mapping, which which is a way for us to specify the dimensions in the iteration space, as well as how the dimensions for each tensors. So here, the first component in the affine map is the dimensions, are the dimensions in the iteration space. So they are I and J. And the second component in the affine map is kind of corresponding to the index expression, index in the tensor, in the high-level DSL. So for tensor A, the second component is I and J. But for tensor B, the second component is J and I because they are ordered differently. And then tensor C only has one dimension, which is I. So in Linalg.generic, we also need to specify the iteration types, which tells whether each dimension in the iteration space is parallel or reductions. Parallel means it preserves the size of the input dimension. Reduction means perform a redux computation and reduce it to 1. So here I put a question here and says, this information looks redundant, and we might be able to derive that from the affine map for the result tensor C in this example. So the third component in Linalg.op is the block of scalar computation. The scale computation, the operation on the tensor is expressed in scalar operations. So in this block, in this example here, the computation, we first perform a multiplication on A and B, which corresponded to the tensor A multiplied by tensor B. And then we perform a reduction, we accumulate the result of the multiplication on tensor C. This expresses the add reduction on dimension J. So the reason that in Linalg.generic op, we need to write out the operation on the reduction is because it supports different kind of operation for reduction. But the DSL itself, we only support the add reduction. So that's how we can use Linalg.generic op to represent a high-level tensor expression defined by the DSL. So here I want to compare the Linalg.generic op, the semantic expressed by the Linalg.generic op with the semantic that we need for the domain-specific language. In Linalg.generic op, the scalar operation is inside, it's applied inside the loop, the iteration space. So because of that, we implicitly got the broadcasting semantic that any operand with missing dimension on the iteration space, its value will need to be broadcast along that dimension. So here, in the first bullet, I want to express that if you literally transfer the expression Cij equal to Aij plus Bi into a Linalg.generic op, you will get the semantic that the tensor B will be broadcast along the missing J dimension. And this is very similar to what we need to implement the PyTACO syntax. And the second bullet it says the Linalg support reduction op. It sounds like explicit reduction specifying by the iterator types, but it actually is, if that doesn't match the implicit reduction semantic, which means if the resulting tensor dimension appear on a source operand, but doesn't appear on the destination operand, it's a reduction. It should be a reduced dimension. So these two should be matched. And Linalg.generic is a little bit more powerful in a sense that it can support reduction operation that rather than the add operation. Why? PyTACO only support add reduction. And then because the scalar operation is performed inside the whole loop that iterates through the iteration space, So we actually got the semantic that is different from what PyTACO needs. In PyTACO, we actually implicit reduction is performed on the smallest subexpression that capture the use of the index variable being reduced. So I have an example here. If we literally translate this expression, di equal to aij plus bij plus ci into a Linalg.generic op, we will get the semantic that we have to broadcast C along the J dimension and then perform the reduction on the whole expression. Why the PyTACO require us to first perform a reduction on aij plus bij and then add the resulting vector to C to produce D. So that's the differences between the two representations. So we also need to use the MLIR-Sparse compilers. The MLIR-Sparse compiler has two important passes, the sparsification passes and the sparse tensor conversion passes. So the sparsification passes take care of the Linalg.generic op that operate on sparse tensors. That means tensors with sparsity annotation. It convert the Linalg op into structure control flow to structure control flow with loops, and then it also insert sparse tensor dialect primitives to allocate sparse storages as well as manipulate the storage. For example, in the sparse tensor storage, there will be memory ref buffers that store the coordinate and values. We can imagine something like that. So the SC structure control flow group basically operate on those memory wrap buffer and perform computation only on the non-zero values of the tensors. And then the sparse tensor conversion passes further lower the sparse tensor dialect primitive, as well as some high-level operations for materializing sparse tensors, as well as performing sparse tensor format conversion into sparse tensor runtime library calls. And the final generate code from the sparse tensor compiler will be able to compile by the regular LLVM compilations. So we have looked at how MLIR supports sparse tensor computation. Now we are going to look at how we take this support and implement PyTACO. So because PyTACO is a Python-based domain-specific language, so we naturally think about using the MLIR Python binding to implement that. And I actually found that MLIR Python binding are very easy to use, and I like that. And it has very simple API for constructing most of the instructions. It's look very similar to the name of the instructions. And there is a decorator called built-in func_op from py function, and it allows you to decorate a function that call the MLIR Python binding for constructing instructions, and then it will generate an MLIR function out of that Python function execution. And then it's very easy to just provide a list of names for the compilation passes to construct a compilation pipeline. So for us, our compilation pipeline, we have to include the sparse tensor sparsification as well as the conversion process. And then there is simple API to just build a JIT engine from a compile module and then start a JIT engine execution by providing the name of the entry functions. The only thing that is complicated is more complicated is the generation of the linalg.generic op. And this is done through Linalg.opdsl, which I will talk about in the next few slides. So Linalg.DSL, the Python binding for that, provide you a way to construct the abstract syntax tree representation for tensor expressions. So it's a tensor expression is represented as a comprehension in Linalg.opdsl. And then the input and output for that whole Linalg.generic op is represented as operand depth. So operand depth, we have to refer to a symbol depth, which is the dimension in the iteration space. And tensor use is an entity to represent operands. And tensor use has to refer to operand depth, either an operand depth or the result of a previous expression. And then it needs to provide a dimension for the tensor. An operation represent as either reduce, apply with the name of the operation, like add, multiply, or prime apply, which is the element operation with the name of the operation. And then this Linalg.opdef is wrapped inside an object called define op callable. So as implied by the name, when you call this object, it will convert the AST represented by Linalg.opdef into a Linalg.generic MLIR instruction. So I have an example to show how the high-level tensor expression on the left-hand side is represented by DSL abstract syntax tree. So the tensor expression is we perform an element-wise multiplication on tensor A and B. Both have two dimensions, I and J. And then we perform an add reduction on the J dimension to produce the result CI. So on the right-hand side is the abstract syntax tree representation along with the Python object that wrap around that. So start from the top is the define op callable, which wrap around the Linalg.opdef. And inside Linalg.opdef is a comprehension that represents a tensor assignment. And the destination of the comprehension is drawn on the right side and is an output operand C with dimension symbol I, and the size is provided by dimension depth, dim depth I. And the expression that assigned to the destination is a reduction, is the result of a add reduction. And the operand for the add reduction is the result for an element-wise multiplication. And the operand, two operand for the element-wise mult are the two tensor used and they are operand depth. They are referred to operand depth A as well as operand depth B. So that's how we represent the high-level tensor operation using DSL. And with this operation, we call the define op. It will help us generate this Linalg generic operation. That's the MLIR Linalg operations. So I don't need to go into the detail of this. So we have mentioned that in order to implement the PyTACO syntax language, we need to identify the reduction expression, the sub-expression that we want to perform a reduction. So in this example here, di equal to aij multiply bij plus ci. If we only literally translate that into one Linalg generic op, we'll get the incorrect result that broadcasts C, a tensor C along the J dimension. So we need to break this into two Linalg generic operation. One calculate the element aij multiply bij and perform a reduction on the J dimension. And then we fit in the temporary result to add Ci to produce the final result. So we need to perform some simple analysis to identify this smallest sub-expression that capture the use of dimension J, which is the dimension being reduced. So since we introduce temporary tensors, there's a question, and what is the storage format we want to use for that temporary tensors? So to answer that question, we use a heuristic. So we use this heuristic to calculate the sparsity for each dimension in the resulting temporary tensors. So the heuristic says if the operation produce a disjunction of zero values of the source operands, like the multiplication operation, and we will we'll use a sparse for the resulting dimension if either source dimension is sparse. So on the other hand, if the operation produce a conjunction of the zero values, then we will use sparse for a result tensor dimension if both source dimensions are sparse. So this is just a heuristic, and we haven't actually done anything to evaluate how effective is this heuristic yet. So with this, we implement the Python classes that are visible in the language. Index var represent a dimension in the iteration space. And mode format is a TACO terminology. It's used to represent the sparsity for one dimension. So a mode format can be either compressed or dense. Then we implement tensors. And then tensor access is tensor plus with the index var expression. And then tensor access can be drawn by operator to compose index expression. So we implement the Dunder method get item for tensor, which essentially handle the syntax a square bracket ij, and that we take care of that. The get item method take care of that syntax, and then construct tensor access object. The set item Dunder methods is when you assign an expression to Cij, for example, it will invoke the set item methods. So we implement the set item method to construct index expression and maybe do some validation, and then store the expression and delay the evaluation of the expression. And then when the tensor also has an evaluate method that is visible in the language. And when the evaluate method of the tensor is called, we start to compile and evaluate the expression and perform the assignment, assign the result value to the tensors. And then in order for to construct index expression, we also need to implement the add and sub and those methods for tensor access. So those are the Python classes visible in the language. And then we talk about when we need to evaluate an assignment. And this is how we do that. So when the evaluate method of a tensor call, we validate the assignment or correct some information to support code generations. This information, so, and then we identify sub-expressions corresponding to the linalg.generic op. Those sub-expressions are essentially for reduction to find the smallest sub-expression that we reduce a dimension. After that, we create an MLIR module, and then we start to look through the sub-expression in the bottom-up fraction from producer to user. Then for each sub-expression, we construct the AST for the expression and call and emit linalg.generic MLIR instruction through the defined op callable objects. And after that, we compile the MLIR module and build the execution engine for the module. And we also need to take care of some data transformation, communication between the Python and C, the execution engine. So we need to use C pointer types for that purpose. And after we prepare the input and output, but first we can invoke the execution engine and then retrieve the result back. So that's how we implement the tensor assignments for the language. I basically finished talking about how we implement PyTACO, and this code implementation is currently in the MLIR test integration directories. So the source code is organized as this way. We implement MLIR-PyTACO, the Py implement the tensor index notation. And then MLIR-PyTACO IO implement the IO functions, tensor IO syntax. And on top of that, we use alias to connect the implementation with the PyTACO language. So that the purpose of that is we only need to, ideally, we only need to change the imported line in order to port a PyTACO native application to MLIR-PyTACOs. And then we also have unit tests for the implementation, and also have tests that are ported from the PyTACO websites. That's the source codes detail. So we are still working on, there are things that we haven't supported yet, like transpose. And we still need to spend time to look at some performance issues. And then there might be more PyTACO functionality that we haven't support and we want to support yet. And also, Art and a few of us are working on a paper for a compiler support for sparse tensor computation in MLIR. And in that paper, we present the MLIR PyTACO as an end-to-end use case. So here we have a link for you to download the paper and take a look. I think I'm done with my, I see some, oh, I missed some questions. Sorry, I didn't check that questions, okay.
I think I answered the questions while you were talking, Bixia.
Okay.
But perhaps there are like live questions.
Feel free to unmute yourself if you have any question, or feel free to ask in the chat. Seems like you've been very thorough, Bixia, in the talk. If people don't have question.
Yeah, great presentation. Thank you so much.
Thank you, yeah.
Yeah, Bob is saying that this is exciting work. Thank you for presenting. So yeah, I agree. Great presentation. All right, if there is no question, then I think we can leave it here for this week. So thank you all for joining. Thanks again, Bixia, for this, and thanks for the work, actually, and landing this in MLIR. I think it's a great addition to the project. I'm very thrilled to see that we get more end-to-end test cases like this one. And next week, Stella is going to talk also about those kind of end-to-end cases with Erie, and in particular, how Erie takes various inputs from ML frameworks, I think. All right, see you next week, everyone.
Thank you, bye.
Bye-bye.
Bye.
Thanks, bye.